Another draft physics video production brought to you by Irritation. Yeah, good enough. So we'll do comments, and who knows where we'll go from there. Let's see what happens. Alright, your thoughts on black holes. Do they actually overcome the pressure between electrons and protons? I guess I would argue that I have no opinion on the existence of, well, the theoretical notion of a black hole where you could take matter and compress it into grapefruits. I say that doesn't happen. There's no evidence that it happens. They're not flying around anywhere locally. There are no small ones. It just doesn't make any sense. Matter doesn't do that. The idea of a neutron star, okay, now you're getting into the realm of realistic possibility in the sense that you could have a mechanism that somehow is able to break, the basic elemental, what we see happen, and breaks it a little bit in the sense that the electrons and the protons, somehow there isn't a disproportion of them. And so I just don't know exactly how a neutron star would manifest, and why it doesn't manifest in other forms besides stars. So again, the argument would be, well, why isn't there a moon made out of neutrons? So I just don't know what the mechanism would be for creating one, I guess is what I'm saying. But the theory that if you did use neutrons, you could get them all closer together. You could get more mass in a smaller vessel if you turned it all into neutrons. The theory would be, as neutrons are electrons and protons that are really close to each other, like compressed atom almost, and that and the protons and electrons in their normal state would be this big. So by having everything in the form of neutrons, having all the electrons and the protons in the form of a neutron, which would be an electron and proton, would give you the ability to compress a lot of mass into a small space, but nothing like a black hole. So I would argue that there's might be neutron stars that are seen as black holes, but they're not black holes. We can't see how small the thing is. We can just see gravity. We can see the effect. Can't see what's actually causing it. It could be, we can't tell the difference between things that are, on the scale and the distance scale. We just can't tell the difference between something huge, really, really big, and something really, really small. We can't tell how big the source is, I guess is all I'm arguing. Just can't do it. So I'd say the theory of black holes is nonsense. Neutron stars, maybe. Okay, so Day, he should change his name back just for old time's sake, is apparently leaving. He's going to a better place, maybe. Not likely, but whatever. No place is a better place, probably. Anyway, this is sort of his last word video, lamenting about his great life and such. It took 4 minutes. Says he does understand quantum mechanics and he's grateful for that, blah, 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 blah. And I don't think he really does, so I don't think his work here is done. Don't think he fully understands. So I think there's lots of arguments to be made yet in terms of proving that. So anyway, apparently got bitten by a pit bull. A pit bull owner getting bitten by a pit bull. Sort of, poetic justice in a way, and not that I wish it on anybody, but I've been there. I have been an attack victim of the pit bull. I was really lucky that I still have a face. He just missed it. Got my shoulder instead. Crazy. The dogs go psychotic, and that's just a fact. And so whatever on that one, I told you so kind of thing. Lots of I told you so's I could do here, but I won't bother doing that because that's totally unproductive. Frankly, I think Hoffler ought to stick around and fight the fight. But his philosophy somehow says it doesn't matter. The future can go to fuck itself. Doesn't need him. He doesn't need to fix anything. Wrong attitude, I'd say. But what are you going to do? Nothing you could say. So anyway, if you want to just, if you have some great reason to live that you can offer them, go ahead and give it a shot. Um, yeah, but otherwise, yeah, it's tough. I mean, I can't, life is hard and unpleasant. So, I mean, I wouldn't wish it on anybody. But it does take a lot of work to learn and understand and be competent to attempt to make the fight. It takes a lot of work to get this battle gear on and do all this crap and blah 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 blah, and just seems a waste to waste that, because somebody else is going to have to do it eventually too. So you're just forcing somebody else to do the work instead of you doing it, and well, that's kind of a shitty thing to do, but whatever, that's the best I can do. So, I don't know if he's going to hear this reply or not. I don't know if he cares now. Okay, good. Not quite the explanation I thought it would come later. Later in the day, I remember you correctly noting that close-up inverse square naturally fails, as is equivalent to modeling two infinite planes. Yes. Your words, not mine, but yes, exactly my words. So, yeah, close enough. Anywho, so the next question I find arising is, remind me if you would please that what differences ordinary materials from magnets. So yeah, why are some things magnetic and why are other things not? Which, seems worthy. I didn't even turn the light on. I'm way behind today. So, I'm thinking of drawing something, but I don't know if that's, Yeah, the idea is that it's a subtlety, like, there's a subtle difference between atoms that are naturally polarized, let's say, and unpolarized. So you could argue that iron atoms are always in some sort of confused state, in the sense that there's always, they just can't, they can't do this equal orientation thing. So I probably should use the blue for the electron, because that's what I've been doing traditionally, and the proton is positive. And so there's an unevenness in the atom itself. So where a traditional atom would have, these kind of proportions, like some sort of balance between the proton and the electron, the iron, you really can't see that. They really are different. It's funny, so I'll exaggerate this a bit more. Alright, so this would be iron, in the sense that there's a disproportion in the atom, an obvious one, where there's one side of the atom, you could argue, if you were to cut a line, is, more electron than the other side in terms of how you would see it. And the idea is that in the iron material, this is such a tiny effect. It's very subtle, but it's there. And the idea is that in normal iron, there's enough agitation of the atoms, they're getting mixed around enough so that orientation ends up going in all directions, and so it's mixed. And when you magnetize, when you expose it to a magnetic field, or you heat it up enough and then expose it to magnetism, you can sort of force all these lines to start lining up, and it is a crystal too, so this gets into a little more complexity. All the magnetic materials are crystals, metals. So then this ends up being what they call a domain, because this is like a fracture in the crystal, and then there's another crystal over here. This might be this way. And there's another crystal that formed this way, and so it's basically just trying to harden the arrangement into things that are lined up. So it's probably more about getting it to recrystallize, all right, in the sense that get the if you can form the crystals in the same geometry, okay, then you'll have a magnet, because everything will be lined up north south, and so the atom will have the same, it'll go up this way, and then the next proton would be here far away, and then the next electron would be close, and it would line up north south, so it would be a bunch of magnets just lining up, north, south. And because of the function of magnets, this ends up being something that will look to the world like something like this. It'll just magnify. All the little magnets will create, in essence, a red end and a blue end for the material itself, and it would be polarize the entire material substance. And so the thing would be is that other atoms of other materials, they just can't create enough of a, enough of that disproportion, or the atoms themselves are just, they move too well, and so they're, unless you get them super cold, maybe they can become magnetic, but they can't become magnetic because they're just moving around too much and fighting each other's magnetism, so they can never agree on an orientation. So they're constantly being reoriented, and they're constantly affecting each other, and so their magnetism can't ever be manifest because it can't multiply, because they can't get all the atoms to participate in the process of making it magnetic. Let's see. So, ordinary materials, magnets. What differentiates ordinary materials from magnets? So the key differentiations, I guess, would say, I think crystals have something to do with it. So the fact that you have to create the domains, but you can't really create in the whole material for some reason. I don't know exactly what that would be, but crystals seem to lock atoms into each other, so it's a geometry that you need, and there's a certain efficiency in the geometry. Like once you've created the domain itself, the crystal can shift, but the crystal itself can't. You have to break it, to break the magnetism. All right, let's see. And how does the material change when a non-magnet is made into a magnet? So anything that's non-magnet that you're going to make into a magnet has to already have this potential. So to me, the two questions are the same question. The more interesting thing is the paramagnetism, I suppose, where the surface atoms end up being arranged, by the pressure you apply, and they react to the pressure. You're imposing a pressure, the pressure changes the orientation of the material on the surface. All right, so I think that answers the questions and such. So yeah, lament and whatever, blah blah. There's nothing, who am I to interfere? I guess I would sort of think that I could have been a better inspiration to the holiday. Been more productive in our interaction, and maybe he'd be more enthusiastic in terms of, there's still fights to be fought. But whatever. I also understand being dead tired and miseries. I have my share of those. So, yeah, it goes both ways. I don't know what to say. I'd rather you participate than not. I'll say that much. Okay. Do it for me? Nah. That won't come off as sincere. I understand that there isn't any density problem now. Okay, no matter how you look at it, your illustrations helped a lot. Well, good. So thanks. It wasn't my intention to waste your time. The only part I don't like is when people are thinking while they're typing, and they haven't really thought it through. So that was the only part that was irritating me, is that if you're just playing around, I've already done enough of that. I've spent 7 or 8 years doing this, okay, having to argue the same points over and over again, having to, some of it quite legitimately, having to defend the theory, and that gets tedious and annoying, and it's not any fun. So I'm sorry if I come off too hostile, but frankly, like I said, if you would have said, I've thought about this and I'm really sure that you've got a problem, well then, okay, I can understand. But you're basically, doing the, saying there's a problem when there really isn't a problem, which is also annoying. You're implying some kind of, you've got something real, and it's just irritating to have to point out again, no, we've been over this. Anyway, it wasn't, so that's bad. I thought you might enjoy answering and thought experimenting, but you are a busy man with a clear goal. Yes, fair enough. Yeah, that's exactly what I said. I'll take your feedback to heart and will reduce the level of noise I generate. Thank you, appreciate it. Just make sure you're making a point, that's all. Or not even make sure, but just a little more than just too casual. Okay, I would just argue that your comments were too casual. I've been thinking about your explanation of magnetism for a decent amount as well recently. I'm having some trouble understanding how laser rays, okay, I don't care for that too much, or diffuse lighting hitting a magnet would affect it in your model. So the fact that light is pretty weak, okay, as a force, I mean, ironically, you know, it's a pretty small percentage of the amount of total energy, and it just happens that it's very good at affecting electrons, though, and creating electricity and stuff. So you could argue how it might affect in terms of creating some charge differentials on surfaces. But again, magnets, sort of by definition, magnetism is something that goes through the whole. You have to really get to the material itself. It's not gonna, you're not going to create a very strong magnetism like paramagnetism. It's going to be a very weak magnetism if it's just on a surface. All right. Understand. Okay. Extra light means extra black force bits, but no extra red ones, right? Yes. But it's a small amount is the problem. I mean, it's, you know, tiny amount of total energy. Just is. Different frequencies and different angles might have different effects. Question mark. They have different effects on the electrons, on the atoms that get hit by the light. So again, if you know, it depends on what the material's made out of. Now, you know, most magnets are composites. You know, if they're ceramic or something, most of the light's going to hit the ceramic material. It's not even going to be hitting the ferrite. So, you know, but anyway, if not, why not? All right. Well, the first reason is because we're fooled by light as a energy. You know, just saying that you need a lot of, like the sun produces a lot of photons, but you know, we know that, you know, per square meter arriving on Earth, it's only 1,000 watts. I mean, it's not, you know, if it was that, that's ideal circumstances. You know, if we had an atmosphere that was vacuum, so it's not very much energy. So I guess that's, you know, I'm just saying, you know, it's not enough energy to affect the magnetic properties in some dramatic way. You need to add more energy. If not, why not? Okay, let's see. Best case is if your model could make some predictions that regular physics doesn't make. Well, like I said, that it does do on other subjects. I've pointed out if you aim photons at the double slit, you'll still get the pattern, completely annihilating Heisenberg. You know, the radar experiment, clearly, I think I'm arguing clearly it's jamming. It has nothing to do with photons interfering with each other. So there's lots of experiments to do. If not, why not? I mean, the interferometer with single photons, these are things they should have already done. Okay, experiments with magnets should be easier to conduct and replicate than radar jamming ones. Well, again, you know, I guess I don't know what to say to that except not really. You know, we'll see. I mean, maybe there are some. I mean, you could argue that some of the ones already done are just being misinterpreted. So again, I can't stop people from misinterpreting an experiment. It's not really about the experimental results. It's about how they interpret those results. like when you have more than one thing, you know, you have more than one magnet in an experiment, and then they do some, you know, they have some, it's like Professor Lewin again, you know, he does a lot of experiments that are quite deceptive, really, when you think about it. He has a nail on a string, right? So you put a nail on a string, and then you have a magnet here, okay, and now you move another magnet into the field. Okay, he sort of implies that the fields are mixing, you know, that somehow these magnetic fields somehow are mixing, and that's why the nail falls off or whatever it's going to do. You know, it gets pushed far enough away where it, you know, doesn't pull on the string anymore. It's not attracted to this magnet anymore. And that's really not right, because what really happens is that when you bring another magnet in, it's affecting the nail's magnetism. So it changes. See, when there's only one magnet, this nail becomes magnetic, you know, north-south, north-south, you know, in the proper configuration. So, you know, it's going to do the opposite of this one, which is it's going to have this red end and then a blue end. But when you bring another magnet in, okay, then you start changing this magnetism, and now the red is this way-ish, and the blue ends up sneaking up over here, and so you start changing the magnetic potential of the nail itself, and its orientation, its domains are changing, and that's why it gets weak enough to swing off. So I'm just saying it's a simple experiment. You can, you know, and people interpret it in different ways. So that's the problem, is how people interpret the effects of an experiment rather than doing the experiment. So there's, you know, I don't know if there's any ways to do the experiment, any subtle ways you can do to prove they're wrong and I'm right. You know, it's kind of difficult. All right, so that might be it for that. So I don't know what this means. I love when people do that kind of crap. And I love it, meaning I hate it, or I have no use for it. I mean, speak English, please. Just, what the fuck is this shit? I'm supposed to know what the fuck that means. Whatever that shit is. Well, I don't. I don't care to know what it means. It's like girl talk or something. Just no interest. Alright, so, I think that's all we've got here. There's not much here. This Cats guy, they had some live show with that baldy Cats guy who's gotten, you know, insanely popular for debunking flat earthers, which, you know, you're saying the world can't be this stupid. I mean, and so they have some kind of science room where, and it's just so trivial. They're playing football, and, you know, it's just so bad. You're just like, oh, fuck this. You know, but they all are so full of themselves. Anyway, horrible. Really. So this looks like a Ken Wheeler video, so I suppose we could do this one. Yeah. Well, let's see if it's the newest one, you know. We don't want to shortchange ourselves, do we? Well, no, let's just go to it. Fuck it. So we'll do some of that.
Now, skeptics say that performance comes at the price of comfort.
Ads you can't block. Ads you can't skip.
We don't follow the skeptics.
I'm not making any money. Here you are.
Hello. It's an absolutist fact that the smaller the space, the higher the capacitance.
It's an absolutist fact. You know, never proven by anything. The smaller the space, the higher the capacitance, which doesn't make any rational sense, right? It's overtly saying the smaller the bag, the more you can put in it. No, that's stupid. It's really stupid. If it were true, you know, life would be so much easier because you could have small batteries with more power in them. I mean, it doesn't make any sense.
Like the further you spread away power lines and alternating current, the more magnetism you could store. If you actually
whatever that is, the more magnetism you could store. So there's no evidence, you know, frankly, that you can store it beyond inside a coil or something where it's reflecting, and so then it has a certain lag time, you know. But that's the way you store it, is having some reflective surface for it to keep bouncing back and forth between. But that's about it.
Fundamentally, also understand the conjugate nature of the universe.
Whatever this conjugate and blah 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 and more, whatever those words are supposed to mean, they're supposed to mean something to us. We're supposed to know that this conjugate thing somehow connected but not connected. What the fuck are you talking about?
You'll realize that everything is force and motion, and
yes, everything is motion, that's for sure. Okay, and forces cause motion, so okay, we'll go for that.
And inertia and
well, inertia doesn't mean too much. That's kind of a nothing word, right? But it's connected to that motion word for sure. Inertia and acceleration. Yes, well, acceleration is a form of motion, but acceleration can lead to velocity or no extra velocity. So that doesn't mean much either. Acceleration just means change. Change in your motion. That's acceleration. So if you're changing your motion, you're accelerating.
There's no exception to this. In the conjugate geometry of the universe.
And it doesn't mean anything. It doesn't say a damn thing. It doesn't help at all.
Is toroidal for force and motion, i.e. centrifugal.
Yeah, so all this centrifugal stuff and starting getting into all this moving crap, so you have a bunch of stuff inside the magnet that's moving, and yet there's no evidence of energy. There's no source for the movement. There's no cause for the movement. We have to explain, right? We came up with a concept of gravity to explain why the Earth is going in this circular path. And you have to explain, why is it doing that? It should go in straight lines. How come it's going in a circle? So we have to explain why. But they don't have to explain where the toroid comes from or the hyperboloid comes from. There's no explanation for why those lines are doing that.
Divergence. This is what we think of when we talk about the magnetic field that actually surrounds a magnet, but people actually don't know what a magnet is.
And I guess you're a people then, because you certainly don't.
I mean, a magnet is quantitatively no different before it becomes a magnet than after it becomes a magnet.
So it's just idiotic thing to say, right? I mean, there's clearly a difference. So, and obviously I would argue the difference is kind of obvious to anybody. Look, if anybody's going to be fair to the little bits of evidence that we have, it's just so clear that the difference between a magnet, a piece of iron that's magnetized and a piece of iron that's not, is clearly, okay, nothing, you didn't break the iron atoms, you didn't do anything, dramatic. But there is a change, a complete change. So, I mean, the non-magnetized iron, is going to look, the inside of it's going to look like a bunch of little stuff going all kinds of counter directions and no orientation, no visible pattern at all. And when it's magnetized, it's going to have a clear pattern. The structure is going to be clearly patterned. Okay, clearly patterned. Huge difference. It's a qualitative difference. The pattern's clearly different. And I mean, this is kind of stuff, there's just so much evidence for the existence of the domains, the fact that the metals are crystals, and that really all you're doing is lining up the atoms, orienting them to be complementary to each other's magnetism. The dipoles are already in the material, and all you're doing is lining them all up so they make one big dipole.
Magnet. So what is the qualitative nature of the magnet? And that, of course, is the fact that it's point source.
Point source. It doesn't mean anything. It's point source. Everything theoretically in the universe is point source in the sense that these little points, these little things, are causing everything. So obviously an effect happens here, and the effect reaches the outside in terms of changing what happens. But lots of these points have to change, and obviously when you make the big magnet, it's not point source anymore, because all the points are lining up to create the new source.
Here we actually have the plane of inertia along these two magnets. Let's say this.
So that doesn't also mean anything. It just means the line you draw where you say, okay, if I cut it here, okay, there's lots of planes of inertia in a sense where you can break the magnet. And clearly there would be a dividing line where the effect is going to separate this side from this side. And how well it filters. It filters more the further away the two poles get, the more they're charged. So, I mean, again, it's more their charge aspect becomes more and more obvious. But it's just a dipole. And really all you're saying is how far apart are the dipoles.
One, and this is a perfect, I'm going to go into
Monopoles.
black holes here very shortly, but I'm going to give you a perfect analogy that I think should actually illustrate it in your mind.
So this connecting, magnets to black holes, there's just no reason to play this wacky game.
And this is an N40 Gauss magnet, and this would be a N55 Gauss or N60 Gauss neodymium.
Right, and so he has no evidence to back any of this crap up where he's going to say that somehow the fields are disproportional, like somehow the stronger magnet doesn't obey the inverse square law or the R cubed law, when of course it does, just as much as this one does. So the force degrades at exactly the same rates, and it's just a complete, he has not one shred of evidence that there's any distinction at all. This just means a higher density of magnetism. That means you can get more magnetism in the smaller space, okay? So if you have two equally sized magnets and they are doped at these different qualities, it just means this is going to be a stronger magnet and it will reach further. It will be stronger at a further distance than this one will be, and that's just a fact. And he doesn't demonstrate how that's not true. He never takes a 40 Gauss and magnet and shows how it has less pulling force, more pulling force at say 1 millimeter than this one does. At 1 millimeter, this one's going to win. This one's going to win. It's a stronger magnet. It's going to win any contest between these two magnets. This one's going to win.
Boron or samarium cobalt, doesn't really make any difference. And when people buy these, most of them are N35 or N40 Gauss, people will make note of the actual spatial nature, i.e. the voluminous nature of the magnetic field that surrounds, say, the N35 or N40.
So he has not cited any of these people. I've never seen anyone cite this at all. None of this stuff. The argument you could make is that these are more expensive. To get more alignment is more expensive, and they might be more fragile. That is, they're easier to lose their magnetism. So they come out of the factory N55, but they might not stay that way because you bang on them a little bit and you get them a little too hot. You do something to them, the magnetism's more fragile. So you could argue that the higher they go with this number, the more magnetism they get out of it. The more dodgy the physical structure of the magnet is, and the more likely it is the magnet's going to be knocked back down to an N40 by just use. So there's no rational theory to what he's arguing here. There's no math to defend it. There's no experiments to defend it. It's just not fucking true. And he's citing it as true. And it's not true.
40 Gauss. And of course, this is what fascinates people about magnets, is the field. And of course, the field is toroidal or donut shaped. And this, of course...
And of course it isn't. It is radial, and it's just there's no donut to be found anywhere, and this only happens to what you put other magnets in the field, what they will do. And they don't create a bunch of lines right next to each other. They create lines distant from each other because they are creating opposite magnets. So as I've pointed out, the simple truth is, the truth that Ken Wheeler's not pointing out, the fact, okay, well demonstrated fact. All right, this isn't even a challenging, you can't argue this stuff. It's just so basic to the function. And yes, regular physics makes a mess of it also. But I mean, what's happening with the field lines? They're absolutely meaningless in terms of giving you an illustration of what the magnet's actually doing. The magnet's actually doing this. Okay, there's a qualitative difference between the force coming out of it. This one reflects protons, this one reflects electrons. That's the fact. Now, regular physics doesn't have an explanation for why that is, but they'll agree. If I put a proton here, it's going to be repelled. If I put an electron here, it's going to be repelled. That's the factual difference between the two sides to the magnet. And so what happens when I put another magnet in vicinity is kind of obvious. If I put another magnet oriented to this magnet and it's not allowed to move into the magnet, I mean, it's not allowed to do what it wants to do, which is just go straight into the magnet. The fact is that it'll orient itself. If I throw a little tiny magnet onto this space, it'll orient itself in the same direction. So if I put it down opposite, it'll flip. Okay, but it's going to orient itself to be the exact opposite. And each little piece of the iron filings will do exactly the same thing. They'll all pile up on top of each other because they'll stick to their attractive ends and they'll avoid their repulsive ends. And they'll create a magnet. So this line, that, you know, this distance, I'm not allowing it to move in, right? So, I mean, it's stuck out here. And the simple truth is, if I drop another piece over here, well, a similar thing's going to happen. Another line's going to form, and the line is going to be exactly the same magnetic orientation, you know. So these magnets, so this line overall, this whole line will end up being a positive at this end and a negative at this end. That's the kind of magnet this will make. So this is going to be the opposite, exact opposite of the original magnet. Well, this other line is going to do exactly the same thing. And what do you see that's obvious about this is that, oh, is that in, yeah, it's in the picture. Okay, what's obvious is that these magnets are going to be repulsive. This one and this one. That's why there's lines. That's the only reason why there's lines. There's no lines of force going this way around a magnet. There's no energy moving this way. This line can be anywhere depending on how thick this material is. So I make this really tiny particles. The lines will be much closer to each other in a different alignment. If I make them big clunky pieces, then there'll be big lines and they'll be far apart. These aren't real lines. There's no force. There's no energy doing this. There's nothing. This is what it's doing. Okay. This is what it's doing. Oh. But anyway, the fact that the orientation of the magnets being created in the iron, the compasses, however you want to look at them, the fact that all the compasses will line up north, 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 north. They'll all be the same wrong magnetism, opposite of the first magnet. And obviously they'll have to repel them. If I can make enough small enough compass needles and put them right next to each other, the compass needles would move away from each other because they're the opposite orientation. Okay. Yeah, don't need that. I don't know how that
Is mass. This is not specifically mass and what we think about it as far as weight or something of that, but we're talking about the actual voluminous nature of the field, how far out it extends, as far as the field geometry relational to, for example, this N40 Gauss magnet. Here we have a north pole, here we have the south pole. We're not talking about pole orientation.
Right, so again, he's implying, he hasn't said it directly yet, but he's implying that somehow this weaker magnet has stronger magnetism at a distance than the stronger magnet. And that is not a fact. It's demonstrated by no experiment. It's just nonsense.
Of course, a magnet doesn't actually have poles. Then we have to get into defining a force vector and the incommensurability.
I mean, it's his own implied experiments where he claims he took his big, giant $1,000 magnet and held it 30 feet from a TV screen and, you know, screwed up the TV screen, implying that, well, you can only do this if you have a $1,000 big, giant magnet. Yeah, well, right. I couldn't do it with any small magnet, could I? From a distance. No, I couldn't.
Of point source, and of course the toroidal geometry that surrounds any magnet is of course the force and motion vector of the field that defines magnetism, and magnetism is the dielectric field.
So again, just more talk. What does that mean? It's the dielectric field. So he points arrows going both ways, which they're not going. If they were going somewhere, they're not going both ways. So it has that messed up pretty well. Well, what is he implying? That the energy goes this way and this way? No, it doesn't do that. If anything, it comes out one end and comes in the other end, as they show in the pictures, which is nonsense, but whatever.
Literally, it is the flip side of the coin, if you will, of the silver of the conjugate geometry of the universe, which is force.
So more conjugate geometry, which is force and motion. Force and motion is not a geometry, okay? Geometry is squares and circles and all that kind of stuff. Geometry isn't force and motion.
in motion. Inertia and acceleration,
Yeah, inertia and acceleration. That's not geometry either. These are huge category errors throwing these words into these sentences. But just gibberish. Just somebody, please, a defender of Ken Wheeler, please explain how force and motion has anything to do with something like geometry.
magnetism defines force and motion. And here we have right here the hyperboloid, or an hourglass shape. We could actually kind of draw the hourglass.
So some sort of implication that something's doing any of this stuff, either that it's doing this swirling up or that it's figure eighting or any of this nonsense. And there's absolutely no evidence for it. Not a single experiment you can detect this at all. Any force, any energy, anything spinning in any direction whatsoever. You can't take a little magnet and put it on a very delicate little string and then make it spin, okay, based on its energy. You have to impose some other external force to force it to do something.
Shape here. This is the geometry of increasing inertia and acceleration. Once again, let's remind ourselves that we're looking at an N40 Gauss or N35 Gauss magnet. And of course, the voluminous nature of the magnetism is the only thing people are interested in. Like if I get a nail this close to the magnetic field of this magnet, it will start to accelerate. People think that's magnetic attraction, but that's ridiculous.
Well, it's obviously well defined as that. I mean, it's fair enough way to use words if attraction's a real concept. I mean, obviously I'm arguing it's being pushed, okay, but it's not attraction. But clearly the effect is that the two things either move towards each other or they move away from each other. Those are the two movements possible. And, that has to be physically accounted for. You have to explain, why do the atoms in the material move? What's causing them to move?
Anything that actually accelerates towards the point source nature of this unique phenomena that people are so amazed by has nothing to do with magnetism.
So again, he just threw in point source, doesn't explain what the fuck that could possibly mean in this context. Clearly the north end is a different point than the south end, and clearly two fundamentally different things will happen to an electron put here, and an electron put here will do two opposite things. What does that have to do with point source?
That's literally dielectric acceleration.
So again, more nonsense, gibberish words. Dielectric is a semi-insulator that can hold charge on its surface. An insulator that holds charge on its surface. What does this have to do with dielectrics? Oh, that's right, nothing.
And that, of course, is not a force. There's no such thing as magnetic attraction. It's completely ridiculous.
Well, it's completely ridiculous to deny the distinction between repulsion and attraction, and those are the two fundamental effects, and so why wouldn't you write sentences saying it's either attracted or repelled? I mean, there's really, our vocabulary only leaves us with those choices. We really don't have much of any other way to describe the effect than to describe it as either moving towards or moving away, attracting or repelling. There's perfectly valid language.
Magnetism, by definition, both denotatively and connotatively, and the correct understanding of the conjugate geometry of the universe, is that magnetism is...
So he just keeps saying these words like they're supposed to mean something. Like if I looked in the dictionary and put the definitions together of the words he said, that somehow those strings of words and sentences would somehow create a coherent understanding, when that would be frickin' impossible.
Force in motion. If you wanted to define true magnetism, that would be what we would call quote-unquote magnetic repulsion. But let's not diverge too far off topic here.
Well, it seems you're way off the topic. That is entirely the topic of a magnet, is the repulsion and the attraction. The fact that one end does it to protons and the other end does it to electrons in exactly the inverse way. That's the signature of a magnet.
Now let's go over to the N55 or N60 Gauss. People say, well, I'm really fascinated by magnets, and I'm going to buy me an expensive magnet, N55 Gauss. The N40 is really cool, but the N55 is definitely going to be a lot better. And I get emails about this quite often, believe it or not. And people will think, well, people don't understand.
Well, why don't you show us one or two of them? You can just take their names out, just take the text, and let's just hear how their experience is that somehow their stronger magnet is somehow not what it should be. But it is close up, but it isn't far away. That somehow the magnet is magically broken in some way, where it's still N55 close up, but it's not an N55 far away. Where do you have any evidence of this? Where can you duplicate this? I mean, maybe you could contact these people and ask them to send me their magic magnets, because I'm saying that they've got to be magic magnets, right? And all they're really doing is complaining to you is they bought an expensive magnet and it turned into a dud. They didn't handle it very well, or they shipped it poorly, and by the time you got it, it wasn't an N55 anymore.
What a magnet is, or what defines a magnet. And they think the magnetism is something wholly separate and unique. You know, that a magnet is quote-unquote emitting magnetism, and it's not. It's not emitting magnetism. It's the actual nature.
It's not actually emitting anything. That's true in the sense that it doesn't actually produce any energy itself. And as I pointed out, so the same is true for everything. Okay, nothing really is a source of energy. Okay, nothing. It's just different ways of filtering the existence of the pressure. So they're just pressure regulators, you could say, or whatever you want to, however you want to term that. But they're filters, and the simple truth is what's happening is this stuff comes in, okay, mixed, all right. And after it gets through the magnet, it comes out segregated. That is, all the blue crap comes out this side, and all the red shit comes out this end. Generally speaking, not all of it, but a higher percentage. And so all the magnet's doing is filtering what comes in. Everything is bombarded by the universe, and everything reflects some kind of part of it in some sense or other. And they can reflect it by absorbing it for a little while and then reflecting it. But the fact is because of thermal equilibrium and all these other laws of physics, all you can do is, you know, this this storage has limitations, and you'll always end up being at some point where just as much as going in is going to be coming out. You can't break those rules, but you can do this. You can take stuff going mixed through you, and when it comes out of you, it's coming out not mixed. And when both sides are doing this of the magnet from all three dimensions, what basically you end up with is something that's reflecting all blue from one end and all red from the other end. And that's the simple function of the magnet. The magnet produces nothing. It just produces a consequence. It just says what comes in will come out. It's just going to come out in a different place. That's it. Red stuff's going to go this way and blue stuff's going to go this way. That's it. You don't need any conjugate geometry. You don't need to screw around with any inertia crap. You don't have to make it complicated. It's just very simple. It's like if I had a material, you know, that would absorb the blue light, and only so all the blue, you know, I had a red and a blue light shining, and so it's purples hitting the surface, and then when it hits the surface, the blue component reflects off one end and the red component reflects off the other. It's as simple as that.
Picture of the ether, the field that actually surrounds the magnet. The magnet's not emitting anything. Actually, quantum idiots actually will say that a magnet is emitting quote-unquote virtual photons or virtual particles, which is completely ridiculous.
Yes, obviously they have to use the word virtual because they have no accounting for where it comes from, because they don't understand that it came from the universe, that the universe is the source of the energy, that there's little bits of momentum coming in from all directions all the time, and all the magnet's doing is just segregating what's coming in. That's the source. So they're right that they're virtual photons. They're right that they're photon-like, that the energy is essentially in the form of photons, and they're essentially radiating from the object. And essentially all the magnet's doing is taking the purple and segregating. All the blue reflects off one end, all the red reflects off the other end.
Ridiculous. This is an arbitrary concept completely dreamt of in the minds of...
So it's clearly not arbitrary. It's an effort to explain the phenomenon within the range of understanding why there's R-squared laws, and, you know, and understanding the nature of charge and the fact that it is a radial force. It's radiating from the object. And the divergence of the force is what causes the weakness at a distance. How much is the force diverging? And in the case of magnetism, the problem is the two sides start mixing, and at a distance you're going to start seeing purple. That's the problem, right? Close up you see all blue and all red. The further away you get, the more purple you're going to see. And the purple means to an electron attraction and repulsion, so it's nothing. And it means to the proton retraction and repulsion, so it means nothing. So it's neutralized at a distance by remixing the force again. So now it doesn't affect a proton differently than it affects an electron, and therefore it won't polarize an atom.
Intellectually drunk people, they're not the inputs or outputs of any experiment ever done.
So this is a lie. They are the inputs and the outputs. That's exactly the point they're making, is that the outputs of the experiment it quacks like a duck, it walks, talks, does all this stuff like a duck. It looks exactly like it's a piece of momentum, a piece of photon.
Completely ludicrous. But let's actually get onto the topic of this really, really strong, really, really powerful magnet, and that people will realize relative to, once they purchase it, and they'll say by their cylinder or bar magnet, similar to that of their N35 Gauss magnet, which has this sort of magnetic field around it. And I'm kind of drawing this improperly here because I want to...
Yeah, it would be improper, it's insane, it's stupid, it's retarded, it doesn't make any sense. So it's just nonsense. It's just completely unproven. No experiment on Earth ever demonstrated the weaker magnet has a bigger field than the stronger magnet. No one ever. It's just a nonsense claim. This is supposed to, again, this guy claims to be an expert on magnets. He has no experiment demonstrating this fact to be true. Not a single frickin' experiment in the history of mankind proving this to be true. It's just such an overt, inaccurate pile of nonsense.
Much space to draw that. What is the issue with the fact that the spatial bubble, if you will, the toroidal bubble that surrounds the super powerful magnet, is much smaller? In other words, you have to get...
So why don't they do the experiment and prove Maxwell wrong, right? I mean, you're just saying, okay, you've got proof that Maxwell was wrong. Okay, his equations completely fail. So you've got proof of it with some experiment. I mean, you'd be rather famous if you could actually prove this to be somehow true, because it would undo Maxwell's equations, would all be garbage. They are garbage, but they're garbage for another reason. They're not garbage because they don't work. They're garbage because they're wrongly premised.
A nail, for example, or other ferromagnetic objects, much closer to the physical magnet of the more powerful magnet. Well, this doesn't make sense. I mean, from their understanding, which is,
the physical laws dictating how these magnets, the force mixes, okay, you go from blue to purple and all that kind of, those laws are reliable and dependable. I mean, they use that science to get to the moon and all that kind of crap. They wouldn't have been able to do any of this crap if this was not true, if they couldn't depend on those laws being accurate and true. So what he's saying is just frickin' wrong.
Humanity is completely unevolved when it comes to understanding field theory. You have to get a ferromagnetic object a lot closer to the more powerful magnet. Well, this should not be the case. The more powerful magnet should have a larger field than, say, our N40.
So again, let's understand, he's hypocriting to his own bullshit. Because he did a video where he had his big giant magnet and he's affecting the TV from whatever, 10 feet away or something. I mean, it was nowhere near what he said. Or something like that anyway. He implied that he did the experiment. Let's say he didn't show it, but he implied he did the experiment, and that he has to, keep the big giant magnet in isolation chamber somewhere because of all its effects it has on everything. So clearly he doesn't even believe his own theory.
Your N35 Gauss over here magnet, but just the opposite is the case, because people don't realize that magnetism is the dielectric field. When you actually increase the power of the magnet, people need to understand that power a la a magnet, when we're talking about N55 Gauss or N50 Gauss, or there's even some...
So again, the power of the magnet just has to do with how well doped it is. So it just has to do with how pure it's able to do this filtering thing. So just saying how much dirt is in the in the purity of it. How much diamond, how much dirt, kind of thing. I don't know how to. It's difficult to get every single atom to play along. So the idea is a lot of them don't play along, and so you're really just deciding how many you've gotten to do the right thing and how many are still doing wrong things, and that's the strength per mass of the magnet. It's nothing that dramatic, and clearly there's no physical laws that would explain why you could have a strong magnet in terms of a well created magnet would somehow have a greater or lesser field anywhere out of proportion to its strength. The strength will dictate how strong the field is at this location is going to be dictated by how strong it is at this location, and there's no way to undo that. The law is just as strong as the laws of gravity. You can't undo those laws. Those are rigid, and they're undeniable by anybody reasonable.
They don't hold very well, but they're in 60 Gauss. Some of these, that magnetism is the dielectric field. When you actually increase the power of the magnet, what you're also doing, proportionally, since we're talking about the conjugate geometry of the universe, and the magnet is not powerful enough to vanish from this universe, what happens is that you greatly increase the dielectric acceleration of the nature, because you can't have one without the.
I just understand. You can do this experiment yourself by just stroking a magnet on a screwdriver or something. And the more you do it, the stronger the magnetism. The more magnetism you put into the screwdriver. And there's a certain amount, is the most you're going to get out of it, and that's what you're going to get out of it. But yeah, one stroke will give you some magnetism, and then two will give you more and more and more and more. And it's just as it appears. The stronger you make it, the further away you can pick up a screw with the screwdriver. I mean, there's absolutely no breakdown in the magnetism based on somehow more magnetism means less reach.
Whatever happens to one happens to the other. By increasing the power of the magnet, what you've done, and power is only proportional to the dielectric. Remember, the smaller the space, the higher the capacitance. In other words, a high capacity or a dangerous capacitor, for example, is very small spatially. The same.
So another statement just completely wrong. I mean, it's just not true. Big capacitors that hold a lot of electricity, a lot of potential, amperage, wattage would be the key word, are going to have to be big. Fact. You can't make small, high wattage capacitors.
Is true, and I'm trying to use this capacitor analogy, which is a reality. It's more space, higher the capacitance in relationship to discussing or painting a visual picture in your brain about the fact that a more powerful magnet has a much smaller, spatially voluminous toroidal field around it.
So again, there's absolutely no evidence of it, no physical evidence to demonstrate that there's anything breaks down in terms of the square laws, the square laws of the strength at a distance. And again, those laws are consistent for gravity, the nuclear forces, for magnetism, electricity, charge. They're all consistent laws. And he's, like I said, he's claiming something extraordinary, and he has zero evidence, not one physical experiment.
The ether then does a less powerful magnet. Well, the more powerful magnet should have a bigger field. No, the power of the magnet is in the dielectric. Everything is the dielectric in any object. Magnetism is a loss of that energy, of that ether.
I say I don't even know why he would assert this. It's so stupid a thing to assert. I mean, obviously you should prove it. I mean, like I said, every experiment in the history of mankind demonstrates a consistency with Maxwell's laws. I'm just saying where you're saying there's an inconsistency. You're saying it's not supposed to be that way. That's not what they should be measuring. Well, why don't you show us somebody measuring differently?
Of that inertia. The more you increase it, and this of course does not work in the real world, but say for example, you are standing in your shower.
That didn't work either.
And you increase the power output from the head of your shower and taking a shower, and proportional to that, of course, your drain only drains via gravity. It does not suck in the water at the bottom of your bathtub. But say, for example, you had a tub that worked in conjunction with the output. By actually increasing the power output, you drastically increase the suction at which the water drains at that bottom of the drain. The same is true analogously.
And again, so how is it true that if I increase the power of the amount of water coming out, that I'm somehow going to decrease the amount of water going down the drain? I don't know. I mean, he's claiming a disproportion, but the shower analogy is also going to work by physical mechanics, and you're not going to change the reach. The more water you force through the same size holes, the further the water is going to travel. You know, the more velocity it's going to have.
With the magnet. This more powerful magnet actually has a smaller magnetic toroidal field around it. Now, let's actually talk about...
So again, he says that, and there's no evidence of it, and it's just bizarre. Why is he asserting it? And he's asserted it over and over and over again. He keeps saying it as if it's important. First off, how could it be important to anybody, except warning people somehow that their N50 magnets aren't what they think they are, when they are what they are, and the only thing they are is maybe more delicate. You know, you can ruin them easier. But so he's making this insane assertion, and yet there's just nothing to back it up.
The black hole. The only reason why all these idiot scientists and relativists and quantum mechanic nut jobs have been...
But again, why would he want that to be true? It doesn't make any sense to any physics anywhere, right? That the more is less. It doesn't make any sense. I mean, nothing works that way. You know, you have more gasoline, your car goes further. You have more, you know, there's just no way to make this example comparable to anything in the real world. So it doesn't work that way.
Arguing about a black hole is that its inherent contradiction only stems from the fact that we have no analog here on Earth. People are confused when we talk about mass. We're not talking about weight, however.
Well, again, and there's no analog here on Earth, and that's sort of part of the problem is that there is an analog for chemistry or atoms. You know, we don't have any expectation that certain atoms can't move freely through the universe. Of course they can all move freely through the universe, so why wouldn't they all be mixed up like they are here? So if there's black holes, if there's other phenomenon, why wouldn't it show up locally if it's a phenomenon? You know, that kind of question has to be asked. And again, the only thing that made black holes even contemplatable as a possibility was the fact that Einstein's math, left alone, you know, before they put in the Lorentz protections against violating the speed of light especially, but other things, I mean, as a concept, all right, you can understand that, you know, if I was to make an actual well on planet Earth, you know, and I was to dig a well, you can sort of understand that, well, the deeper I go, this pressure gets insane, okay? And I'm not going to be able to make the walls of the well thick enough to stop this pressure from just smashing it, because this pressure is going to be so frickin' high. So a regular well has a real limitation. You can't dig a well to China. It just ain't going to happen, because you're not going to be able to make any well material that's strong enough to withstand the pressure that's going to be imposed by all of this mass, okay, gravitationally pushing down, which ends up being pushing this way and this way from all directions, but literally converting the pressure into motion in any direction that will allow the pressure to be equalized. So any emptiness will be, it will collapse like a implosion from all directions, because all the pressure, even pressure down this way, will end up going that way. But anyway, I don't want to get into that. The point is you can't you can't physically do it. But Einstein's perception of doing this stupid bent fabric thing, which only works in 2 dimensions anyway, it doesn't even work in 3 dimensions, so it's useless. There's no planes, you know, where you constantly pile up all these bent fabrics, as if you can understand. So in 3 dimensions, they describe it completely as I'm describing it, as a convergence, as force just moving in dead straight lines towards the center of gravity. So that's how they teach the subject of this bent space. And this force, because they're not saying it's a real force in the universe made out of little real force bits, they can make this pressure infinite. Okay, there's nothing to stop them from just making an infinite amount of pressure, because they have an infinite well that they can dig. So they can just go forever down this well hole. They can make it any size they want to, because they're not having to account for real energy, for something that might run out, where you'll actually run out of pressure. And the argument I would make is this: of course that happens. There's a point where you have all the mass that absorbs all the energy, and you can't add more. By adding more acceleration here, you can't add more pressure here. Okay, so it runs out, and so you can't make it. Oh, I can make it bigger, and I can make it bigger, or I can put more mass in it. I can make the mass more compressed, or add more mass to the size of the object, and it doesn't matter. So that's Einstein's bullshit. So it doesn't have anything to do with any physical thing in the rest of the world, though. Nothing else works that way. We don't have any infinities lying around. So that's the bogus nature of their logic, is that they somehow can just compress matter infinitely. And there's no logic saying you can do that you can push electrons as close to each other as you want. No logic at all.
Weight is often interchanged equally with that of mass. We think mass is weight and weight is mass. But what if a magnitude was non-existent? So let's take, for example...
So throwing a word like magnitude in is as if we don't have enough fudging on words like mass. Like we don't already have a problem with vocabulary and understanding the difference between rest mass and moving mass and all of this other bullshit. And so he's going to throw a word like magnitude in, like that's supposed to mean anything. And it can't mean anything. What do you mean magnitude? What is that?
A single weight, let's say a 1 pound lead weight. And remember, the most important thing that we have to understand is that the only reason anything has volume in the universe is due to magnetism, and magnetism only. The one thing
So again, that's just kind of silly, right? The reason why things have volume is because there's protons and electrons, first off, and they repel each other, and that forces distance between them. So that's one reason there's volume. Okay, I mean, a kind of an obvious one. And obviously there has to be some mechanism that's creating the repulsion, and I would argue that's the force, so that's obviously got some volume to it. But everything that has mass has volume, and everything that we call a thing has mass. And so, I don't know, we don't need to really do all of this, right? Well, let's see, he's going to draw lines going into the center.
Really, you learned in school or high school or college is that every atom, and this is what they said, every atom is 99.99999, etc., etc., etc. percent, they say, empty space. In other words, this is an atom, right? It's basically, there's nothing here. Well, that's not true. The air inside the balloon, or the radius in picometers of every atom, is due to magnetodielectricity. In other words, every
So magnetoelectricity. So we got some new kind of electricity. Electricity is a phenomenon, right, where atoms share pressure. So you have to have atoms, you have to have a conductor to conduct the electricity. That's electricity. We only see sparks because they're going through the atoms in the atmosphere. No atmosphere, no sparks. I mean, this is just idiotic.
atom obviously is a dynamo, and it's actually generating magnetodielectricity. And
well, whatever. The fact that it's a dynamo, in the sense that I would argue when it's got velocity, it's got a little motor in it. It's using the laws of physics to propel itself perpetually, like a piece of force, because it's taking advantage of an imbalance that's trapped inside of it. But, I mean, clearly the volume inside the atom is understood by electrons and protons being in a relationship to each other because they're exchanging something, either repulsion or attraction. By conventional physics, they would say the virtual photon is either attracting or the virtual photon is either repelling. I mean, obviously, I think you have to make a real force bit. But anyway, but I've explained all that, so no point in getting into it. But obviously the volume of the atom is just based on the fact that the electrons and the protons are repulsing each other, so they can't take the same space. They have to have a distance between them. And that's the volume of the atom.
volume, if you will, of every...
But it's full of nothing. The empty space is empty except for the forces moving through it.
atom. This is our little tiny nucleus in here.
There's somethings and then there's nothings.
They're infinitely smaller than that.
So anyway, this probably isn't going anywhere, and I've probably done enough. So till the next time and such. Like I said, he's not gonna say anything new. It's the same old gibberish. Probably. Come on, you know it, I know it. Same gibberish. We've already done enough to point out he's full of shit, so there's just no point in pointing out more shit.